Hello, my name is Thijs Dhollander, and today I will be talking about interpreting some of your diffusion MRI findings, namely those of neurite or fiber density changes. So the emphasis here is really on density metrics, and we'll come to see this is way more tricky than you probably expect. I'll be making use of these type of diagrams you see here, wherein this kind of square represents a voxel, and these little dots represent axons coming in and out of my screen. So for example, this might be a voxel in a control subject, whereas this might be a voxel in a patient that has suffered some neurodegeneration or something like that. Alright, so techniques to measure neurite density or fiber density. There are many, because that's what we do in diffusion MRI. We develop many new models. I'll just name a few for example. So NODDI, from NODDI you can get a neurite density. A little bit longer ago there was the CHARMP model. From that you could get an axon signal fraction. And there's also the apparent fiber density metric from spherical deconvolution techniques more recently. But this list is of course just a few examples. These are all slightly different, they all have their unique assumptions, that's why they're different models. But in the end they all aim for something similar, and that's to estimate the density of axons in a voxel. So with density I mean the total amount of axonal matter in a voxel, which is a combination of the axon count and the individual axon volumes. So it's as if you blended up all axons and then you just measured their joint volume in a voxel. That's what I mean by the density of axons. In this presentation I will mainly use the apparent fiber density, and I will call it FD for short, but the general topic of the presentation and the conclusions extend to all these different density metrics just as well. Okay, so apparent fiber density or FD then. Well, it's pretty cool because within a single voxel, of which you see one right there within a brain, we can get actually multiple fiber densities for each different bundle visiting this voxel. So for instance, here you might have the corticospinal tract, you might have the SLF, and there's also the corpus callosum going left-right, and in this voxel you get what we call a full wide matter fiber orientation distribution, looking a little bit like this. And we can get very specific fiber density measurements for each of these fiber populations, and that allows us in analyses, for instance, to detect that in a patient group maybe this lobe here is affected compared to that one, so the SLF has suffered some damage, whereas the corpus callosum and the corticospinal tract, they remained intact. So this offers multiple advantages, but one of them is specificity. We can assign it to this population. Another one is that classic tensor metrics like the fractional anisotropy can actually get it wrong. So in a voxel like this one, where the patients actually suffered some damage in the SLF, you will see that the tensor from DTI actually has a higher FA in the patient population. Long story short, this is due to the crossing fiber situation that the tensor model cannot handle. So that's pretty cool, but of course we need to formally measure these fiber densities and somehow analyze them. And even though in each voxel we have a continuous fiber orientation distribution, what we do is we extract its peaks. And these peaks are shown here in this middle panel, and these peaks we call fixels. So fixels refer to fiber populations in a voxel. So in the background you got the voxel grid of the image there, but on top of that you see individual fixels, and there can be multiple ones in a voxel, as you see when fibers cross. There can also be voxels, like here in the ventricles, that have no fixels at all. So that's the fixel grid. And then for each fixel we extract the size of the lobes of these FODs, and that will become our fixel-wise fiber density metric that you see here in a hot color scale. And as you can see, in certain crossing scenarios, the two fiber populations can have a different FD. It's pretty cool, but how do you analyze that? Well, there's a framework for that, as always. I'm not going to explain how this all works today, but this is called the Fixel-Based Analysis framework. And Fixel-Based Analysis is pretty complicated, but conceptually it's pretty much the same as a voxel-based analysis. So in a voxel-based analysis, you typically start by either creating a population template or using a template from an atlas maybe. and you would register all your subject images to this template to make them voxel-wise comparable. Then you would typically smooth your images, you would perform stats or cluster stats, and in the end you would end up with a p-value map that shows you where the differences are, the significant regions of voxels. So that's VBA. FBA, Fixel-Based Analysis, is the same thing, but then for individual fiber populations within each voxel, that, as I mentioned before, we name pixels. This is pretty complicated to do in practice, so that introduces some new image processing challenges, and that is exactly the reason why this diagram on the left is apparently such a nightmare. Okay, but what you need to extract from this slide in the end is that Fixel-Based Analysis is essentially voxel-based analysis, but for these pixels, fiber populations in a voxel. So what does such a result typically look like? Well, here is one of a control and a patient population compared, and the pixel-wise fiber densities have been statistically compared, and here you see the outcome of the analysis, which is a p-value map. It's a little bit tiny, so we're going to zoom in a little bit, and we're going to zoom in a little bit further on that area right there. And there you can see these individual pixels. The ones that are pitch black, they were not significant, so their p-value was larger than 0.05. Whereas the ones that are in the rest of the hot color scale, especially all the way up to white, they are significant, or in white, highly significant pixels. And the neat thing is that here we can see that actually the cingulum is significantly affected in this patient population. But for instance, the corpus callosum, even though it crosses the cingulum, you see a lot of black pixels here that are actually not affected at all. So we can be fiber specific. So that's Fixel-Based Analysis in a nutshell. I'm not going to talk much more about that. It exists, you can do it. The literature is there. This has been published since 2017 by David Trefelt and colleagues. And last year we also wrote a very extensive review paper about this called Fixel-Based Analysis of Diffusion MRI, Methods, Applications, Challenges and Opportunities, which tries to summarize just about everything we know about Fixel-Based Analysis to date and explain it in a little bit less technical jargon, so you can actually be inspired to how you can use it on your own data. All right, back to fiber density. So Fixel-Based Analysis can analyze this, but we set that aside for now, and now we're going to focus on these fiber density metrics. The title of the presentation was that fiber density changes are hard to interpret, and that is because fiber density is not everything. Okay, let's start with this example. Well, here you see two voxels in two populations. And if I were to ask you, are there any differences? Probably you would say no. And you would be right. The fiber density in both of these voxels is the same. But those are only two tiny voxels. And these tiny voxels, they are part of a wider context. And if we zoom out a little bit further, and in this image now, a single blue square there is a single voxel, and the gray dots are the axons still. So we see that maybe one of these voxels here, compared to one of those voxels there, indeed has the exact same density. And actually throughout this entire fiber bundle, we see the same kind of density of axons as we see throughout this one. So with voxel-based analysis, or even with our fancy Fixel-based analysis, we would first register these to each other to overcome the differences in location and size of the bundles. And then we would compare their densities, and we would find no differences, because the fiber density indeed is not different. Yet, if I were to ask you between this and that bundle, is there a different number of axons in there? Obviously, yes, but the different number of axons is clearly not present in the density, it's present in the overall size of the bundle, or more specifically in what we call the fiber bundle cross-section. Because here we actually cut through the bundle like we would cut a cable, and we look at its cross-section. And if we look at the FC, the fiber cross-section, we would see that the FC is larger here in the control population and maybe smaller in the patient population. So the FC is decreased and therefore the number of axons is decreased, even though the density is not decreased. So this is an aspect we should actually be looking at. That's the fiber cross-section. So fiber cross-section is a little bit similar to what you would do in tensor-based morphometry or voxel-based morphometry, which you probably already know. Because there we also measure differences in volume, typically of gray matter, but it could be any other tissue in the brain. So for instance, in patients, you might have this example volume of 1 voxel of gray matter, whereas in the controls you might have 2 voxels of volume. So somehow in the patient, the volume is smaller than the controls, which is something that we would report. Now, if you do a Fixel-based analysis of fiber bundle cross-section, it gets a little bit more complicated, but the technique can handle this. Because again, here we would have a single voxel of, or single volume voxel of axons running like this. And here we have 2 voxels. Do we want to pick this up as a difference in fiber cross-section? Well, no, because the number of axons here and there is exactly the same. The difference in volume here is a difference along the length of the axons, and we don't want to pick that up. And the Fixel-based analysis will do just that. If the difference in volume is along the length of the fibers, it will ignore it, so there will be no difference in fiber cross-section. However, if we kind of rotate the situation and now the axons are running up-down here, and then we compare it to the bottom, now we can see there is effectively a difference in the number of axons by means of a difference in fiber cross-section, because the density in these voxels is still the same, but the cross-section is different. So that's what this picks up. But again, essentially, Fixel-based analysis of fiber bundle cross-section is kind of the same thing as voxel-based morphometry, but adapted for Fixels, and it gets a bit more complicated, right? Okay, now we can put all of this together because now we have the concepts of fiber density and the concept of fiber cross-section. Let's say, for example, again, in a control population, we start with this situation here of a bundle mapped on a voxel grid. So let's say the fiber density goes down, we might end up with a bundle like this. Same size maybe, but lower density in axons. And we can measure that. Alternatively, the fiber cross-section might have gone down, even though the density maybe remained the same thing. Yet in the end, there's also less axons. So interestingly, the situation here with lower FD and the situation here with lower FC, in many ways they are similar. They end up with less axons. And actually in this example, the number of axons here and there are actually even the same. So in terms of how the white matter is, or how much the white matter is damaged, this is the same. But we do have the specificity to distinguish whether that's due to a decrease of fiber density or a decrease of fiber cross-section. We can even put these two together, and that's what we call the fiber density and cross-section metric, FDC, which is computed as simply the product of FD and FC. And for example, in this situation here, you can actually see the density went down, but the cross-section also went down. Whereas the fiber density metric would pick up some of that effect, and the FC metric would pick up also some of that effect. The FDC picks up both. So the effect size here would actually be almost twice as much in FDC. However, don't be mistaken, even though here there was a decrease only in FD, it also counts as a decrease in FDC as well, because FDC is FD times FC. So if just one of these two goes down, the FDC also goes down. But if both of them go down, then the effects stack together. So the FDC is in many ways more sensitive because it picks up more in all these three scenarios, but it is, on the other hand, less specific. And therefore you need to look at the FD and the FC separately. Okay, that is the whole setting. FD, FC, and then there's also FDC. Now we're going to play with this and we're going to do some exercises. So I hope you've been paying attention. So research scenarios, and we'll do this just like in real life. We'll do research and we're going to do some experiments, and we're going to write a paper with some paragraphs. All right, for example, let's say we have two cohorts, controls and patients, and we're going to do a simple cross-sectional analysis. So we want to look at fiber density because we've seen that this measure exists, and we're going to test it. And we hypothesize that the FD in our patients is lower than the FD in our controls, maybe because we suspect some neurodegeneration, something like that. So when we decide what we test, we write that up, and that's essentially our method section in our paper, right? Methods, we say like, oh, this is the thing we test. It's pretty simple. You decide, you write it up, and this is the thing we do. All right, we run the actual experiment, and we happen to find that there is no FD decrease, nowhere in the brain, nothing at all. So that's the bit we also write up in the results section. Up until this point, I would say this is all pretty simple. Yes, you have to do the whole analysis, but the results just pop out and you just report them. You know, a robot could do the same, technically speaking. But then comes the real challenge. How do we interpret this? You know, what do we write in our discussion section? Some people tend to replicate their results in the discussion section. I find that rather boring. You better can go a little bit further if you understand your metrics well. All right, decrease in FD was tested, was not found. How do we interpret it? Well, here's a few options. We could say, well, the patients apparently show no reductions in axonal matter. Or in other words, you know, interesting for a discussion section, there was no damage in the patients, or there was no degeneration in the patients, something like that. That would be one way to write it down. It would be interesting. We talk about degeneration, we talk about damage, we talk about real world concepts, and we move away from just saying FD. So we're writing a real discussion section here. Alternatively, we could say, oh, we gotta be a little bit more conservative. We're just going to say the patients show no microscopic reductions in axon density. You know, we stick pretty close to FD here. We say like, oh, axon density. We don't talk about degeneration or damage or these high level concepts. So which of these two would you write in a discussion section? So I'm going to give you a little bit of time to think. If you're watching this on a video, hit pause now, I would say. Otherwise, think quickly. All right, I hope you've made up your mind. The question is, how are we gonna figure this out? Well, you know, let's use those diagrams we had before. Let's try and picture some scenarios, and let's see the other way around, whether the scenarios we can picture, and we're gonna picture them here in this white space, whether they are compatible with our findings. And then we can see whether they actually, well, are a sensible explanation for those findings, right? So here's one scenario. Controls, patients, and the density seems to be the same. The cross-section seems to be the same. Is this compatible with finding no FD decrease? Yes, the FD is not decreased. What could you write about this? Well, yes, we could say there is no damage, no degeneration. All right. But can we be a bit more creative, and can we picture other scenarios that go with these findings, but that somehow don't go with this interpretation of no damage or no degeneration? Can we challenge ourselves? Is there something we have overlooked here? Well, obviously there is. I hope you had been paying attention throughout the previous part of the presentation, because this is literally from that part. So this is a scenario where indeed the fiber density between controls and patients is the same, but the cross-section is decreased. So this is something that can indeed go with those results after we have tested that question there. So we cannot say based on the findings that there is no damage or no degeneration, because maybe the cross-section was decreased. So where is the pitfall in all of this? Well, it's right there in the methods. We did not test for an FC, a fiber cross-section decrease. And it seems pretty straightforward now because I just introduced you to the concept, but there are many studies out there, not necessarily of fiber density, but just for example, using the NODDI model with neurite density, which is also a density, and they would have not looked at the fiber cross-section. and they would have found like no decreases in neurite density and say like, yes, there's no degeneration or something like that. So this is something really to take into account. You need to look at the fiber cross-section to get the full picture. All right, okay, we know this now very well. We're not gonna make this mistake again. Next time we check for FC, okay? All right, next scenario. Now we're going to do a longitudinal analysis with 2 time points. Both of the time points are from the same patient group, so both time point 1 and 2, they're already patients, one's early after diagnosis, and the second time point a little bit longer term. And we're going to test whether the fiber density in the long term of these patients is decreased, whether basically over time they suffer some neurodegeneration maybe. But we're not going to get caught out. We're going to check the same for the FC, whether the FC is decreased in the long term versus the early time point. That's the methods here. This time we find that there is effectively an FD decrease. Significant FD decrease is found. But we find no FC decrease. That's the results. All right, how do we interpret this? Well, let's say we could say again, the patients undergo over time some reductions in axonal matter, damage or degeneration. Probably inspired by this FD decrease bit in there, right? Seems sensible. And this time I'm not going to give you a second option. I'm going to ask you, can you imagine something else? Is this it? Is this the thing you're gonna write in the discussion? Or are we overlooking something? Okay, giving you some time to think. All right, we're gonna take the same approach as before and visit some scenarios. So here's a scenario, early to long term. The FD decrease is shown here. FD is indeed decreased, and the FC is indeed not decreased. So this scenario here is a very obvious scenario that is compatible with these results. Based on this, I think we could safely write that indeed there are reductions in axonal matter, less axons, so there is degeneration over time, or damage, or whatever your context is. But can we think of something else? Well, I'll give you this scenario. In this scenario, indeed, the fiber density is from here to there decreased. And we checked whether the FC was decreased, and we found no FC decrease. Is the FC not decreased? Indeed, the FC is not decreased. It is increased, and we had not checked that there. But the FC has increased. How does this make sense? Well, the number of axons here and there is actually exactly the same. There's just more space in between the axons there. Maybe this could be a scenario where the patient suffered a condition that longer term caused some inflammation. So basically fluid was building up between the axons, and actually the whole bundle was swelling due to that. So that's not degeneration. The axons are not going away. They're still there. They're just more fluid in between. And due to that, the density decreased in each voxel, but the fiber cross-section increased and perfectly compensated for that. So there is no degeneration. What was the pitfall here? Well, we did not check for an FC increase. Sizes can also increase due to the space between the axons, of course. Pretty tricky. Needs to sink in a bit, but again, we're not going to make that mistake again. Sizes can increase. Next time we check for FC increases, right? Okay, next exercise. Very similar, again, longitudinal analysis, early and longer term patients. This time we test, is the FD in the long term decreased versus the early time point? Is the FC decreased? And we're not gonna get caught out, is the FC increased? We also ask statistically. We do that, and this time we find something different. We find that there is no FD decrease based on this question. And we find that there is a significant FC decrease. So FC is not increased, but it is significantly decreased. And FD seems to not have decreased. Okay, same question. How do we interpret this? Well, the patients undergo reductions in axonal matter, damage or degeneration, our default go-to sentence, right? Probably based on the FC decrease. Did they suffer degeneration? The FD didn't go down, but the FC did. Or is there again something else you can picture here? Well, by now you get the picture. There's probably something we overlooked. Let's go and visit some scenarios. So this could be a scenario, right? Early versus long term, the fiber density has not decreased. It's the same here and there, but the FC indeed has decreased. And based on that, indeed, axons are lost. So we could say, yeah, A, degeneration. But is there something else that we have overlooked? Well, how about this? Early on we got this. We asked, is the FC decreased? And we found it indeed. The fiber cross-section is decreased. But we also checked, is the FD decreased? And the FD is indeed not decreased. No, the FD is increased. And again, we did not check that. Again, we missed something. But what does this even mean? How can the FD increase? Well, again, in this and that scenario, the number of axons is the same. Yet this time, from early to long term, the space in between the axons somehow collapsed. So this is something that might happen where these patients were already diagnosed. Maybe they were already degenerated to begin with. So axons were already missing and there was already a lot of empty space in between. And then between our early and our longer term time point, maybe atrophy happened. And these axons actually collapsed together. So the size of the bundle decreased, but between these two time points, the actual axons themselves didn't degenerate further. So we can not write A. It's no degeneration. The number of axons here and here is actually the same. So again, we got caught out and we needed to check that the FD could increase. So this is really complicated, and at all times you need to think about all possible transitions. So these are the diagrams I showed you before. We're going from here to there would be this decrease in fiber density. From here to there would be this decrease in fiber cross-section. And from here to there, fiber density and cross-section. But you need to look at all the numbers and you need to consider things like this here, for example, axons collapsing. So you need to look at everything. And it can get even more complicated. I'm not going to discuss this example in detail. But the gist of it is that from healthy here to axon loss, only these orange axons have suffered. But then atrophy happened and the whole situation of the crossing fibers collapsed. So the blue bundle here never ever got affected, yet you will see its numbers change due to how the orange bundle created extra space and the whole thing collapsed. So it can actually get quite complicated. For this example and many other examples, I do refer you to a review paper. So this is in there, some of the previous stuff is in there, and you can take your time and look at it in detail. All right, some conclusions here. What do you know? Interpreting fiber densities happen to be pretty tough in the end. So the main pitfalls we've seen today are ignoring the size of the structure. So the fiber bundle cross-section, the FC metric, we ignored that at the start, and clearly we should always be looking at that to get the full picture. Not considering or testing the opposite effects. So decreases but also increases of density metrics, but also of fiber cross-section or of volumes in general. We should look at decreases and increases to see the full picture. If you don't test for them statistically, you don't know and you might be missing scenarios. So most of this then happened due to stuff or space in between the axons. So edema or swelling or inflammation might cause the volume to increase but the density of axons to decrease. Or the other way around, atrophy might axons collapse. And if they collapse, the density might actually go up even though the cross-section goes down. So you need to think of the full picture again, also the space in between the axons. And then I haven't even touched upon this, but an absence of a statistical significance doesn't prove an absence of any effect. So whenever we found no differences, well, we actually didn't find that. We just failed to detect a difference. You also need to take that into account. So even when doing everything right and considering all the things like we just have, there's often still a range of different explanations that are technically compatible with a given finding. So our specificity is inherently often limited. And that's just an inherent limitation of diffusion MRI data and the methods that come with it. Some of these bits we can just not technically overcome. So ultimately, the only way to get beyond those limitations is to rely on a few assumptions. That's what you typically do if you need more specificity. You make some assumptions. And that's not per se a bad thing, because oftentimes you do have a sensible context. If you hypothesize that inflammation might happen, and you find that the density goes down, but the cross-section goes up, then you got your explanation right there. You can use this information, of course. So at this point, I would be asking whether you got any questions, but this is a video. I'm not here in person today. If you got any questions, just feel free to email them at me. And I thank you for listening. Enjoy the rest of your conference.